Okay, good morning, everyone. I understand there was a little bit of misunderstanding between the rooms and so on, but I hope everyone is here already, and whoever wants to come after, that's fine as well. I'm Professor Manas. I come from Case Western Reserve University, which is in Cleveland, Ohio, in the US. And I was invited here to talk to you about mixing. And I prepared 3 lectures. I'm not sure we'll be able to go over the 3 lectures, but I would rather than going through the 3 lectures and you leaving the room and saying, oh, what was all that about? I would prefer to go slowly. And if you have any questions, just raise your hand and I would like to answer them, rather than me talking and you sort of not understanding what's going on. So please interrupt me and I can try to answer the questions which you have. Okay, so again, good morning and welcome to this course. Today I'm going to talk a little bit about mixing fundamentals, and I divided the talk in 3 parts. In the first part, we are going to talk about important mechanisms, fundamental mechanisms of mixing. In the second part, I'm going to address a little bit the problem of mixing equipment and optimization of mixing equipment for design and processing. And in the last part, I thought that I'll give you an overview of mixing in nanocomposites. I would imagine that you are very much interested in nanocomposites. And so I'm trying to give you also an overview of nanocomposite material and mixing as relates to nanocomposites. So, this doesn't, it works on my screen, but not here. Okay, so it should work now. Okay. So mixing is one of the most common operations which is intended to reduce a system non-uniformity. And we know mixing from ancient time, and I saw that this is particularly relevant in a place like Cheshme with such a long history. So people used mixing in ancient times actually to mix their grains. Mixing is also very much used in paintings, so mixing of colors. We are talking also about mixing as stretching and folding of viscous fluids. Here is an example of turbulent mixing when you see those clouds and a tornado is approaching. But you can also find mixing in everyday life when you want to make your famous recipe cake. You also need to deal with mixing. Now, the equipment which is used in mixing started with like a pestle and a mortar. Obviously, painters used all sorts of instruments to mix their colors. But nowadays, we talk about mixing in industry, and here is an example of a bamboo mixer or an extruder, or actually also more recently mixing on microchips. And so those are the materials to be mixed, and here are the instruments in which we can realize mixing. The big question is that mixing really an art or is it science? And certainly most of the people will tell you that mixing still is an art. And if you think about, all those companies producing tires which keep their recipe of mixing so secret because they say that it's only them that know how to make an excellent tire. And everything lies in that art of mixing. Well, I would claim that it is art, but in a certain way, we start more and more to understand the fundamentals of it, so it becomes more and more science. So here is an ancient book of how the pharaohs did mixing in their kitchen. Another example is a book on Roman cookery. Well, obviously, there is the art of mixing drinks. And here is a book which I have edited a number of years back, which is talking about mixing and compounding in polymers. So why is mixing important? So just referring to one example, which is the mixing of fine particles in material processing, you see here that we talk about mixing in coatings and in fluid stabilizers and in paints, in tires, in making the most fancy yachts, right? So in all of those, not to mention the structures, the big structures and the aeroplanes and the cars and so on, mixing remains always a very important component of any production and of any industrial operation. So let's talk now about fundamentals. So if I think in terms of mixing particulate solids into a matrix, usually those fine particles tend to agglomerate. So we start with a system in which we have big agglomerates which are not evenly distributed in the matrix. And so if I want to think only in terms of the reduction in size of the minor component, in other words, the reduction in size of the agglomerates of particles, or the reduction in size of droplets of an immiscible fluid, the mechanism involved in that reduction in size, it's called dispersive mixing. Now, however, if I'm concerned only about evenly distributing those agglomerates into the matrix, so I'm not concerned about the size, but just to distribute them evenly in the matrix, that mechanism is called distributive mixing. And the goal of any mixing operation, any properly conducted mixing operation, is to get to a stage where the minor component is dispersed at a very fine size, and it's also evenly distributed in the matrix. So any mixing operation comprises two important phenomena. One is dispersive mixing, breaking down the agglomerates or the droplets to the fine size. And the other one is distributive, which means distributing all those particles or droplets of a second fluid in the matrix. And that is called distributive. So we are going to address today both those mechanisms. So if we think about the dispersive mixing is the breakup of the minor component or the agglomerates along the processing stream. So here is just the schematics of an extruder or a sonicator or a roll mill or any other mixer. And so we start here with an agglomerate. Okay, please come in. It's okay. I'm not offended. Okay, so dispersive mixing is the breakup of the agglomerate into very small components. And when I talk about very small components, it doesn't have to be the primary particle. As long as we reduce the size of the agglomerate, that phenomena is already dispersive mixing. And I told you before why is dispersive mixing important. And so here are again a few examples of using fumed silica in coatings, or for rheology control, or for corrosion, or for in the yachts, or in tires, and so on. So in general, we add additives to the polymer in order to control and tailor some properties. And so most of the important industrial products will have not only the polymer, but they will have fillers. And the breakdown of fillers into the smaller components is dispersive mixing. So if we think in terms of what are the steps involved in dispersion of a particulate solid in a fluid, first of all, we have to incorporate the filler in the matrix. So the first step is incorporation. The second step is the breakup of the agglomerates into smaller particles, and that step is the dispersive mixing. We talk about the distribution of those particles in the system, so that's the distributive mixing. And you know that unfortunately, sometimes we also need an extra step, which is the stabilization to prevent the flocculation of the particles. Now today I'm going to focus primarily on the dispersion aspect. And so going to the steps, we are going to look at how an agglomerate is breaking down into the smaller particles. So if we think about the dispersive mixing process, what is the essence of it? So an agglomerate is held together, all those primary particles are held together by cohesive forces. Okay? Why do they stick together? Because there are cohesive forces. In the process of mixing, our goal is to overcome those cohesive forces. So how do we overcome cohesive forces? We put those agglomerates into a media and we apply forces, okay? And those forces are called hydrodynamic forces. So the dispersion is really a battle between the cohesive forces, which try to hold the agglomerate together, and the hydrodynamic forces, which try to break down the agglomerate. So in order to understand dispersive mixing, we need to think in terms of what parameters or what factors are affecting both cohesive forces and hydrodynamic forces. When would the agglomerate break? When the hydrodynamic forces exceed the cohesive forces. It's only under those circumstances that the agglomerate will break. And so we need to consider those factors affecting both cohesive forces and hydrodynamic forces. Okay, so if you think in terms of the kinetics of the mixing process, how can we qualify mixing? How much we reduce the size of the agglomerate? So any kinetic model which describes dispersive mixing will be a change in the radius of the agglomerate with time. And that change of the radius of the agglomerate in time will be proportional to the balance between the hydrodynamic forces and the cohesive forces. So we can say that it will depend on how much the hydrodynamic forces exceed the cohesive forces. Now, if those forces, the hydrodynamic forces, are much larger than the cohesive forces, then the agglomerate will shatter, will rupture, okay? Rupture or shatter. However, if the cohesive forces are only slightly less than the hydrodynamic forces, then the process of mixing will be an erosion, meaning that you will scrap from the outer side of the agglomerate particles. So it will progressively decrease. Now, if I think about the agglomerates of particles, the agglomerates are porous, okay, because there are primary particles which are assembled together. So we can actually look at the hierarchical structure of the agglomerate and say that they are comprised of the smaller units which are called primary particles, which are clustered together into aggregates, and the aggregates are also clustered into the agglomerates. So we can distinguish between the micropores and the macropores in the agglomerate. The size of the primary particles is in the nanoscale, but the size of the aggregates are hundreds of nanometers, and the size of the agglomerate is even larger. It can be microns or millimeters. And we can define the overall porosity, epsilon, of the agglomerate, and phi is the solid volume fraction of the particles in the agglomerate. Now, as I told you, there is always this balance between the hydrodynamic forces and the cohesive forces. And the hydrodynamic forces, meaning the forces which try to or tend to break the agglomerate apart, are dependent on the strength of the flow field, right? But it will also depend on the geometry of the flow field. And you probably heard that elongational flows are much more efficient in dispersive mixing than simple shear flows. So keep in mind that the strength of the flow, but also the geometry, or how much elongational flows we have in the system. Now, the agglomerates, so the cohesive forces, will be dependent on a number of factors which influence the agglomerate, the cohesivity of the agglomerate. And they range from the density of the aggregates, okay, the structure, they are high structure or low structure, the surface area meaning how small or maybe larger the particles are, the morphology of the particles, if they are spherical or rod-like or any other shape, and also the surface treatment. So all those parameters will affect the cohesivity of the agglomerate. But there is something also more than that which is going to affect the overall dispersion process. And that is the fact that because we have a porous structure, okay, the fluid, the matrix, will infiltrate inside the agglomerate. And that infiltration of the fluid inside the agglomerate will change both the cohesivity of the agglomerate, and it will also affect the way in which the stresses are transmitted to the agglomerate. So just pause here for a moment. So let's see, I was talking maybe a little bit too fast, but what did you learn? What did I learn so far? I learned that I have to worry about the cohesivity of the agglomerate, okay, and all the factors which affect the cohesivity of the agglomerate. I learned that I have to worry about the flow field in which I try to disperse the agglomerates. So it's both the strength of the flow field, but also the elongational versus the simple shear flows in the flow field. And on top of that, I have to worry because I have a porous agglomerate. And the fluid will start to penetrate inside the agglomerate, and that will affect both the cohesivity of the agglomerate as well as the way in which I transfer the stresses from the matrix to the agglomerate. Okay? So we are good so far. Any questions here?
What is called hydrodynamic?
Okay, so hydrodynamic means the stresses. So let's talk about flow. Okay? Imagine that we have an extruder and there is flow. In the extruder, due to the flow, there are forces which act on the agglomerate, and those are called hydrodynamic forces. Any other questions?
It's a fluid, so that's why it's hydrodynamic forces, right?
Yeah, because it's transferred from the fluid.
Well, it can be also melt.
Well, yes. Yeah, absolutely. It's the melt. Melt is also a fluid. It is a fluid. It's a viscous fluid, but it is a fluid. Okay? So when you apply force or deformation, it will flow. That's a fluid. Okay? Any other questions?
Could you open a little bit the strength and this part, the right side?
To describe it?
Yes, strength and geometry part. I couldn't get it.
Okay. So here is an example of a simple shear flow. And so in a simple shear flow, you characterize the flow by the shear rate or shear stress. The higher that is, the higher the strength of the flow field. Okay? The more forces you apply on the agglomerate. The geometry means that here it's just schematically, and I'll show you in a moment what I meant by it. But we did experiments in the lab in which we apply those forces on a simple shear or in an oscillatory device. And there are differences, okay? But the idea would be it's different if you try to mix in a single screw extruder or in a twin screw extruder or in a bamboo remixer. That's the geometry of the flow field. Okay? Any questions? No? Okay, then let's go further. So our objectives are to understand and characterize the dispersion filler mechanism. And I would like also to talk a little bit about the influence of surface treatment on the dispersion. And when I'm talking about surface treatment, I will talk about the traditional additives which we use in industry, but also about the so-called smart additives. And I will introduce a little bit the idea of those smart additives. All right, so now let's show you how we did experiments in our lab. So what we did is we prepared agglomerates of controlled density, okay, such that we understand better what's going on. So we prepared those agglomerates of controlled density, controlled porosity, and we also controlled the size. And then we did the experiments in two types of flow fields. So one was a flow field, which is a cone and plate, which is the usual type of experimental device. So in this type of device, we have a uniform shear, and we have a controlled flow field. So in other words, we can calculate what is the stress in the field by multiplying the viscosity of the fluid with the shear rate. And we did that experiment in a controlled flow field in which we had a transparent wall, such that we can observe the motion and the size of the agglomerate as it changes in time. So that was a control type experiment. So basically what we observed is that we started with an agglomerate of a certain size, and the forces which we applied were not that high, and so we controlled the mechanism to be an erosion type mechanism. All right. And here is just a picture of that agglomerate as it erodes. So we have here the rotating cone, the agglomerate, and here we can observe the detachment of small fragments from the outer surface of the agglomerate. We also did experiments in an oscillatory shear device. So here we have two parallel plates, one oscillating and the other one stationary. And we observed the same mechanism of erosion of the agglomerates. And so here is a picture of that agglomerate as it is eroding. And you see very clearly the detachment of fragments from the outer surface of the agglomerate. So let's talk now about the dispersion kinetics, which is the balance between the hydrodynamic forces trying to break the agglomerate and the cohesive forces trying to hold it together. And we characterize the dispersion because we have those controlled experiments. We can measure how the size of the agglomerate is changing in time. So we define the kinetics of erosion by the change in time of the radius of the agglomerate. So again, we have the cohesive forces versus the hydrodynamic forces, and you have seen that before, and the infiltration of the fluid. And so let's look in particular at how do we characterize them further. So first of all, here we would like to address the issue of the agglomerate cohesivity. So we can test the agglomerate cohesivity. We made a device which is a split cell device in which we put the agglomerate of a certain density, and we try to break it apart, and we measure what's the force required to break it apart. And so, and that is in tensile. So we use Rumpf formula to calculate the tensile strength of the agglomerate, and that will be dependent on this A, which is a Hamaker constant, depends really on the nature of the particle. But this cohesivity of the agglomerate will depend on the solid volume fraction of the agglomerate, okay? Which means that the solid volume fraction plus the porosity gives you 1, okay? So the solid volume fraction is exactly 1 minus the porosity of the agglomerate. It depends on the primary particle size. It depends on a minimum distance between the particles. And so one can actually measure that agglomerate cohesivity, and we usually did those measurements as a function of the density or porosity of the agglomerate. We can also measure a different type of cohesivity in shear. So in this case, we make an agglomerate of a controlled density, and we try to push that needle inside the agglomerate. And we measure the force which it takes for the needle to penetrate inside the agglomerate. And so we can calculate the shear strengths of the agglomerate. The other one was the tensile strength. we can calculate the shear strength measuring the force and the depth of cone penetration inside the agglomerate. So those are just ways to characterize the cohesivity of the agglomerate. And now here we plot the strength of the agglomerate, okay, as a function of bulk density. And obviously, if we increase the bulk density, we increase the strength of the agglomerate. What is very interesting here is the fact that for the same bulk density, the shear strength is order of magnitude higher than the tensile strength. Okay? And that means that the agglomerates will break in tensile, not in shear. Okay, so those were controlled experiments. And now we look at other factors affecting the cohesivity. So we look, I told you, there are the morphology of the agglomerate which affects the cohesivity. So first of all, we look at aggregate density. So here is a high aggregate density, and the picture here shows that. And this is a low aggregate density, okay? So the low aggregate density is in blue, and the high aggregate density is in black. And what do I see? At the same overall bulk density, which one is stronger? And why? Let's think together why. Why? Okay, so, okay, one more thing to think about, okay? So I look at those two pictures, right? And if I would have asked you before I show you the results, which one is more cohesive, the high density or the low density? You will say low? You will say high. I can.
No.
High density is stronger, right? That's.
Northwise, in the case of high aggregate density, you are breaking the macropores.
So, what is happening here is that at the low, for the same bulk density, so if you look at those pictures, the number of small primary particles is the same. I put them like on purpose the same. But the contacts, okay, the contacts for the low aggregate density are more, right, than for the high density. The contacts between the aggregates. And so that's why the tensile strengths will be where higher? At the low aggregate density, right? Because you have more contacts between those aggregates. Okay? All right, now let's move. We talked about high structure and low structure. So high structure are more branched. Low structure are more compact. Which one will be of higher cohesivity?
More branched.
The one which are more branched, right?
Yes.
And so if I look at the same bulk density, the high structure will be higher than the low structure. Now what happens if I put those agglomerates in a flow field? So I did the experiments, not me, but the students did the experiments in a cone and plate, okay? And we applied the same hydrodynamic stress, meaning that we controlled the shear rate and we know the viscosity of the fluid. And so what do we observe here? If we have equal porosity, for the powder, right? And we plot here the decrease in time of the radius of the agglomerate, okay? Which one erodes faster? The higher, but in this case, I compare low structure and high structure. So the low structure will erode faster than the high structure. Why? Because the low structure is less cohesive than the high structure at the same bulk density. If I look at the aggregate density, okay, and here again I plot how much the agglomerate is eroding. Which one is eroding faster? The high density, right, aggregate. Remember that we talked about that? So all I'm trying to say is the following. I show you that the cohesivity of the agglomerate is the one which is really determining how much I can erode. And different structures, low density, high density, or low structure, high structure, they behave differently at the same agglomerate porosity or density. Okay. Now we go to different surface area. So we have a high surface area meaning smaller primary particles, or a low surface area, higher size for the primary particles. So here I plot the tensile strength versus bulk density for a low surface, an intermediate one, and a high one. So at the same bulk density, which one is the highest cohesivity? The high surface area, right? The smaller the particles. So now what do we expect when I put them in a shear device? Which one will erode faster? Low. Okay? So this is the result, okay? So here I have low, medium, and high. So the least cohesive agglomerates will disperse more. Okay, everyone is with me?
What are the actual surface areas?
What is?
What are the actual surface areas per gram, meters squared per gram?
Oh, for those, you are asking me a question which I cannot really answer. What we did is we took, for instance, carbon black. And there is carbon black of various surface area. And we compared 3 different grades. Okay, then it was silica. So we had fumed silica and precipitated silica. And so they are different primary particles. But we did, I mean, here is silica, but we did it, trust me, also with carbon black and all different. So it depends on the grade, but I cannot tell you a number because I don't remember those numbers. But you can look in, we publish papers on that, so. Okay, now I come to the very interesting point, okay? So everyone is fine so far? It's a little bit hot here, but other than that, we are fine, right? Can we control maybe the temperature?
It's like the lowest one.
That's the lowest one? Okay. Okay, then that's the lowest one.
Is it hot for you?
For me, yes, but
In US, they setting is too low, I think.
oh,
I'm
okay.
freezing in US.
Okay, so I'm used to the freezing. But that's okay, don't worry, okay? I'll be fine. I promise I will finish. Okay, so let's look at the effect of matrix infiltration, okay? Do you remember I told you that the agglomerates are porous, so we'll have fluid coming into the agglomerate, okay? That's the infiltration of the fluid. All right, so here I take the example of calcium carbonate of a certain solid volume fraction, and I measured what is the tensile strength of that calcium carbonate, and I use fluid of viscosity 60 pascal seconds. And I put those agglomerates and I let them soak for 10 minutes. So I put them in the fluid, let them soak 10 minutes, and I did the experiment for erosion in the cone and plate. And you see that nice curve, right? Change in the size of the agglomerate in time. Then I said, okay, let's soak them for 25 minutes. I did again the experiment. What do I see? Decrease, right? So what do you think? Why does it decrease?
The matrix went into the box.
Right, and?
And it built more cohesive forces.
Perfect, because there are liquid bridges, right, between the particles, and so it builds the cohesivity. So if I will show you only this, you will tell me what? What should I do in order to increase dispersion? Don't let them soak, right? Just erode them immediately. Okay, that's what you will tell me. All right, now let's see something else. Okay, so that was calcium carbonate. Now I look at silica. Okay, so in silica, with silica, I did the same experiment. So, soaking for 3 minutes, it's this one. Soaking for 10 minutes is this one. Soaking for 1 hour is this one. So, how is that? Okay, I'll tell you. I mean, I'm here to tell you why. But isn't that strange?
Yes.
The calcium carbonate was one behavior. The silica is a totally different behavior. And so we said, why is that going? What's going on here? All right, so now we did also other type of experiments in which we take a dry agglomerate and we observe the infiltration of the fluid inside the agglomerate. So that was silica with PDMS. And what we did, we measured the thickness of the infiltrated layer as a function of time. So in other words, we want to calculate the rate of infiltration of PDMS into silica. And so we defined a model for the infiltration, okay? And this is also published. So we can calculate at every single time what is the thickness, using that model, the thickness of the infiltrated layer. Okay. So what did we find out? We found out something very interesting. So what I am plotting here, and that was supposed to be animated, but you trust me without the animation, right? It was very nice, like, but it doesn't work. Okay. So look at this delta R over R0. Delta over R0 is the thickness of the infiltrated layer divided by the radius of the agglomerate. Okay? And we plot that as a function of time. So obviously, as the time is increasing, the thickness of the infiltrated layer is increasing. So if I look only at the purple. Then I did the experiments of dispersion, right? And I did them at different times of infiltration. Okay? And what do I see here? I see that after 3 minutes, this is in second, okay, I have a thickness of the infiltrated layer which corresponds to the thickness of the layer which was eroded. Okay? And if I go further, I have more infiltrated layer, I erode more, okay? And so on. So what do I see in this case of silica? That the thickness of the infiltrated layer corresponds exactly with the thickness of the layer which I am able to erode. Hopefully this will match. Okay. So here is a schematics. So this is the infiltrated layer. This is how much I erode. So I have a removal of the infiltrated layer surrounding the dry core. And that mechanism of dispersion we call adhesive failure. Okay. What's happening here? So if I look at the partially infiltrated agglomerate, and here is the fumed silica, I have in the infiltrated region a rearrangement of the powder such that what is happening if I look at it? So here, as the fluid is infiltrated, it is rearranging the structure of the infiltrated layer. And I have a dry core, which is not yet penetrated. And it is at the wet to dry interface that I have that rearrangement without enhancement of powder cohesivity, okay? So in other words, imagine the following. I have this agglomerate, the fluid comes in, and it rearranges the structure of the infiltrated layer and sort of pulls it from the dry core. So the interface between the dry core and the infiltrated layer becomes weak. And when I apply the shear, forces, the hydrodynamic forces, it will detach exactly at that boundary between the dry and the wet. Okay? So the wet-dry interface is a weak point, and that's where the erosion will occur. But what happens with calcium carbonate? So in calcium carbonate, I showed you the exact opposite phenomena. And so can I think about why in one case I have a rearrangement and in the other I don't? So in order to do that, I can calculate actually the capillary pressure on the powder, okay? So that capillary pressure depends on the porosity and the surface tension and the particle size. And that's that was defined by Schubert in 1975. So here is a picture of how the fluid penetrates and the capillary pressure exerted on the powder. All right. Now, if the cohesive strength of the agglomerate is higher than the capillary pressure, so tau C is the cohesive strength of the agglomerate, and that should be in shear, okay? Because those are shear forces. For calcium carbonate, I can calculate the capillary pressure is 181 kilopascal. And the shear strength, so the cohesive strength of the agglomerate in shear is 191 kilopascal at that particular density. So obviously, which one is higher? The cohesivity. That's why it does not allow rearrangement, okay? And what it does, it just reinforces that outer layer with liquid bridges. What happens in the case of silica? If that cohesive strength in shear is less than the capillary forces, so for fumed silica, the capillary force are 350, and the cohesivity of the fumed silica in shear is 150. So it's less, right? So if it's less, it will allow rearrangement. And if it allows, so it allows the particles to move to rearrange, and that's why I can create that weak spot between the dry and the infiltrated. And that's why I detach exactly how much I infiltrated. All right. So we learned about two different mechanisms. One is cohesive, and which means that I do not have rearrangement of the internal structure of the agglomerate, and adhesive, where I do have rearrangement. Okay, let's talk more. So I told you that the infiltration is important because it alters the filler cohesivity, and I gave you an example of that, but it also can change the way in which the shear stress is transmitted to the agglomerate. And you probably are very familiar with ways to change the cohesivity by using binders. Yes or no? In particular, what we want to do is affect the surface properties, okay? So here I'm showing you an example of a coupling agent. And I use those in silica. So silica is hydrophilic. I want to disperse it into a matrix which is hydrophobic. So what I would like is to change the surface properties and the interactions between the matrix and the powder. So want to disperse hydrophilic silica into a hydrophobic SPR. And what I did is I used this traditional binder to treat the silica to make it more hydrophobic. And here are some results of the experiments which were done with different amounts of treatment for the silica. So this is untreated silica. Again, those are erosion experiments. 5% treated powder and 10% treated powder, okay? Huge changes in the dispersion by using surface treatment for the silica. All right, so surface treated silica show enhanced disbursement.
Sorry, you treat first and then you make the agglomerate?
Right, yes, yes. We treat first, then we make the agglomerate. We affect the cohesivity and also the way in which the stresses from the SPR transfer to the silica. All right, but there is also another way to affect the the dispersion by using the so-called smart binders. And so the question which we asked ourselves was, which parameter can we use to control dispersion? So we are using what is called a responsive binder. So in those responsive binders, I control the cohesivity of the agglomerate by manipulating an outer parameter, such as temperature. So I use a binder which is responsive to temperature. And by manipulating the temperature, I can manipulate dispersion. All right, and so what we used was a polymer which is called PNIPAM. And this has a lower critical solution temperature. And so above the lower critical solution temperature, I will have hydrophobic interactions. Below, I will have hydrophilic interactions. And so the lower critical solution temperature is 32 degrees. What we did is we treated the powder with that particular, now the other thing here, before I go on, I should tell you also that I can use the cross-linked version of the PNIPAM, and that one is also exhibiting changes with a change in temperature. Basically, the swelling degree is a function of temperature. So this is like a gel, and so if I look here, if I decrease the temperature below the lower critical solution temperature, the gel is expanded. Below, if I increase the temperature above the lower critical solution temperature, the gel is shrinked.
You mean the temperature while in mixing?
Okay, so I'm just showing you the polymer now, okay, not what's happening during mixing. So I just want you to know that I have a linear polymer, and I also have a cross-linked polymer, and they both have those transition in morphology based on temperature. And there is a lower critical solution temperature for both of them, okay? So this is just the notion of the binder itself. Okay, so let's see what happens if I treat the powder with this binder. So I am coating the silica particles with the linear PNIPAM, okay? And I hypothesize that the forces between the silica particles will become a function of temperature. So at 25 degrees, the binder is hydrated, okay? And there is reduced interactions between the particles. At temperature above the lower critical solution temperature, 68 degrees, the binder is collapsed, and so it will make the forces between the particles stronger. Okay? That's what is happening. Let's see if I use the cross-linked polymer. So if I am at 25 degrees, this cross-linked PNIPAM is swollen, okay? And it will somehow hold the particles together. When I raise the temperature at 68, the cross-linked polymer will collapse. And what will happen is that it will have some destructive forces on the structure of the agglomerate. And we were trying to use both of them in experiments to see how that will affect the dispersion. So here are the results. First of all, we saw that if we have hydrophilic silica, and we use that linear polymer, we see no difference whatsoever between dispersion at 25 or 68. However, if I use hydrophobic silica, what I see is that the dispersion is much higher at the temperature below the lower critical solution temperature, and it becomes much suppressed at temperature higher than the lower critical solution temperature. So let's think about it. So a temperature which is above the lower critical solution temperature, how is the linear polymer, the PNIPAM? It's collapsed, right? And so being collapsed, it will enhance the forces between the particles, cohesivity increases, dispersion decreases.
I would like to ask one thing. In hydrophobic environment, the NIPAM will be in a phase difference form because itself is hydrophobic at the temperatures lower than the LCST.
So this is just the characteristic of the silica. Okay, so you can get silica hydrophobic or hydrophilic.
No, but NIPAM will be also in phase difference at that state. Are we talking about only silica hydrophobic?
Yes,
Okay.
only silica hydrophobic. Yes, yes, yes. And here is just an example that if I use no additives, there is no difference in the dispersion behavior. So here is the cartoon illustrating what's happening. So in the case of hydrophobic silica, at temperature below the lower critical solution temperature, the binder is hydrated and it reduces the interaction between the particles. At 68 degrees above the lower critical solution temperature, the binder is collapsed and it's allowing strong interaction between the particles. Now, in the case of the PNIPAM, which is cross-linked, the behavior is quite different. So first of all, what do I see? I see that at a temperature below the lower critical solution temperature, both in the case of the hydrophilic silica and the hydrophobic silica, the dispersion is much lower. At temperature above the lower critical solution temperature, the dispersion is much, much higher. So what happens in this case? So I put that gel inside the particles. And so at temperature below the lower critical solution temperature, the gel is sort of holding the particles together. Okay? And that's the 25 degrees. So I don't see too much dispersion. However, when I raise the temperature, the gel shrinks. And the forces due to the shrinkage of the gel cause some disruption in the agglomerate structure, and I can improve tremendously dispersion. So that's just another schematic. It's the same story again. So here is sort of a summary. So in the case of the linear polymer, the linear PNIPAM, for the hydrophilic silica, I see no difference. For the hydrophobic one, I see much enhanced dispersion at temperature below the lower critical solution temperature, and at temperature above, I have the collapse of the binder, which means enhancing cohesivity, decreased dispersion. If I use the hydrogel particles, the cross-linked particles, I see the opposite. Both for the hydrophilic and the hydrophobic silica, I see that at temperature below the lower critical solution temperature, the gel is expanded and it holds together the particles. When I raise the temperature, the gel is collapsing, disrupting the internal structure, and I see enhanced dispersion. Okay? All right. So here is again a summary of what I just told you. And so, in summary, regarding dispersion, what did we learn? So we learned that the agglomerate structure and intrinsic cohesivity will affect the dispersion, both mechanism and kinetics. We see that the fluid infiltration inside the agglomerate will change the dispersion because agglomerate is a porous structure, and the fluid infiltration can change both the cohesivity as well as the transmission of forces. We saw that in the case of using binders which are temperature dependent, we have those thermoresponsive binders, and we can control the dispersion kinetics by changing the temperature at which we do the dispersion. So, in terms of mechanisms, we learned about the cohesive failure, meaning just the breakup of the agglomerates. We talked about adhesive failure when we have a fluid which is rearranging the internal structure of the agglomerate. We saw that the onset of the adhesive failure appears to be governed by the ratio between the capillary forces and the strengths, the shear strengths of the agglomerate. And here I'm giving you some references. So this is all about dispersion, okay? Now, we should take a break. You think so? Okay, so we'll take a short break. When we come back, we talk more.